So in our final example, we're asked to find the horizontal and vertical asymptotes of this function. So let's start with the vertical asymptote. So if you recall from my previous video in the notes, I stated that the first thing you should do to find a vertical asymptote is to look for the domain restrictions. And what we're talking about here are discontinuities. Discontinuities are found especially in a rational function. From here, they're going to be found in the domain. So we're going to write out the domain as x squared plus x minus 2, and we're going to set it to 0 because that's where our discontinuities are going to be found. Of course, for a root function, some function, we know that x is going to need to be greater or equal to 0. Otherwise, we'd have a complex or imaginary function. So just be aware of what type of problem you're working with so that you can find those vertical and horizontal asymptotes. So in this case, let's continue on, and we will find that this is -2. So first term multiplied by the last term, and then we're going to have 1 to the middle term, and we're going to find two values that when multiplied give us the top, and when added together give us the bottom. So we're going to find that this is -1 and 2. Therefore, we have x minus 1 and x plus 2 equals 0, such that x cannot equal 1 and x cannot equal -2. What I want to do now is I want to plug each one of these values in. And the reason I want to do that is that when I plug in f of 1, I want to know, do I get division by 0? Division by 0 would tell me that I have a removable discontinuity, which we've been calling a hole in my graph, the graph of the functions curve. So I want to do that for each value. Since we already know the values that create 0 in the denominator, we already have those values. We have 1 and we have -2. We really only need to plug those values into the numerator now to see what we end up with. So let's do that. So f of 1 for just the numerator, we're going to have 2 times 1 squared plus 1 minus 1. These cancel, and we're left with just 2. So we do not have 0 over 0 when x equals 1. We have 2 over 0. All right, so the next one would be f at -2. We plug that in, and we will end up with this is going to be 4, this is going to be 8. So we're going to have 2 times 2 is 4 times 2 is 8 plus 1. So we're going to end up with basically 9 over 0. So again, we do not have division by 0. There is not a removable discontinuity. And we can see that another way. So as the book does it, they set it up as the limit as x is approaching, and they set it up for each one of these values, 1 and -2. So beginning with 1, we have 2x squared plus x minus 1 over x squared plus x minus 2. We already know that it's going to have a discontinuity, and it's not going to be a removable discontinuity. So now we're trying to find out, is this going to be a vertical asymptote? I can tell you it is. It's definitely going to be a vertical asymptote. And let's just go ahead and reduce this. So we are going to find that the limit as x approaches 1. For the numerator, we're going to go ahead and multiply this out. So we're going to find this as -2, and again, in the bottom is 1. And for this one, it's going to be, again, 1 and 2, -1. I do this a little bit different than most, so we're going to end up with 2x minus 1 multiplied by 2x plus 2. And then I'm going to reduce my factor of 2, which means I end up with 2x minus 1, x plus 1. Okay, so for the numerator, I have 2x minus 1 times x plus 1. And that is going to be divided by, and we already solved for the denominator. We know that it is x minus 1 times x plus 2. And as you can see, we do not have any like terms that are going to factor out of the denominator and numerator to help us with this. So we know that the limit does not exist for the limit as x approaches 1. It does not exist. Further, taking this reduced form, we will say that the limit as x approaches -2 for 2x minus 1 times x plus 1 over x minus 1, x plus 2. Again, we find that the limit does not exist. If you're not seeing that, we can use our direct substitution property that states that we can plug in our values that x is approaching. And when we do that, we find that -2 here creates 0, and 0 times that other product gives us division by 0. Here, we found that if we plugged in 1, we'd end up with 0, which would be division by 0. So we know that as the limit of x approaches 1, or the limit of x approaches -2, that the limit itself does not exist. It's not approaching a particular value. So what is it doing? So I do need a little room here. So I'm going to get rid of all of this. And that's not what I want to do. And I didn't see the book doing this, so I just want to show you that there is a way to use our tables, but thinking of it as a number line. And we'll put our value of 1 here. We'll call this 0, and this -2. And this is called the sign test. And what this does is it allows us that when we find that the limit does not exist for our values of x approaching 1 and x approaching -2, we want to know what's going on. We want to know what, we know that there's a vertical asymptote. That is for sure. But we also want to know, what is that graph doing as it approaches those values? So in this question, it's not actually asking us that, from what I remember. It was just specifically asking us, where do the vertical asymptotes exist? Where are the horizontal asymptotes? Well, let's go ahead and see what happens. So for the sign test, we're just looking at these values as we approach from the left and from the right. And for 1, as we approach from the left and from the right. So if we choose values that are really, really, really close to each one of these, so just left and just right, it's just like our tables. So basically we'd say for -2, a really close value to that would be -2.25. So if we put that in, we find that as we approach from the left, the value we get is negative. And as we approach from the right, the value we get is negative. So if I have a value just a little bit bigger than -2, so 1.75, and I input that into the function, what I'm finding is that I'm getting values that are going towards negative infinity on both sides of -2. So I could actually say that the limit, because they're both going in the same direction, for x as it approaches -2, for the function, for this function f of x, is going to be negative infinity. That's how we find our negative and positive infinities. So when we are finding those limits for x approaching -2, we use tables, but this is just telling you how to figure that out. What is the sign as you're approaching your value? What is the sign itself? That tells you when there's a vertical asymptote what the graph of that function's curve is doing as it approaches the value. So I hope that makes sense, and we'll do it one more time with 1. So for 1, as we plug our values in that are just a little bit less than 1, and I encourage you to try this, just take a value like 0.75 and plug it in for x. And I think you'll find that as you do that, you're going to end up with a positive. And you're actually going to find that you have a positive value on both sides. And I apologize. The limit as we approach -2 from the left is actually a positive. I apologize for that. And as we approach from the right, it is negative. They're going in opposite directions. So the limit as x approaches -2 for the function f of x does not exist. They have to be going in the same direction. So my values that are less than -2 were positive. My values that are a little bit larger than -2 are negative. So for 1, I am sure about this. They are positive on both sides. So the graph of this function's curve, as it approaches 1 from the left and right, it is definitely heading towards positive infinity. So we could say that the limit as x is approaching 1 for the function f of x is positive infinity because they're both going to the same direction. So to answer the question, where are the vertical asymptotes? Well, just by taking the denominator itself and then plugging the values in to make sure that we don't have division of 0 over 0, which would mean that there's a removable discontinuity, meaning that there would be a term in the numerator and denominator that would reduce. Because we found that we did not have that, we can say that our vertical asymptotes are at x equals 1 and x equals -2. So that is the solution for our vertical asymptotes to this function. So now we're going to look at our horizontal asymptotes. So that's a little bit different, of course. We're setting this up and saying that as the limit of x, and we'll start with positive infinity, as x approaches positive infinity for 2x squared plus x minus 1 over x squared plus x minus 2. And our horizontal asymptotes our end behavior of our graph. And again, one way that you can kind of check with a rational function or a polynomial is to find the lead coefficient or lead term. In this case, it's going to be the highest variable for the numerator and denominator. In this case, it's already lined up such that 2x squared over x squared is going to equal our graphs, the graph of our function's curve's end behavior. So this will reduce to just 2. So we're guessing right now. I don't want you to use this as how you solve these horizontal asymptotes, but we are going to say that as we start solving this, we are probably trying to find a value 2. So let's see if we can do that mathematically. And to do that, we are going to take the lead variable or highest power variable in the denominator. And in this case, it is x squared. And what we're going to do is we're going to multiply the top and the bottom, the numerator and denominator, by 1 over that highest power denominator. And when we carry that through, we find that each term is now going to be divided by x squared. And we have to do that for the denominator. So we have each term divided by that x squared. From here, we need to, again, remember rule number 6 states that anytime you have a constant and they show 1 over x, and then they show 1 over x raised to the nth power, and they said that it is constantly getting closer to 0 for the limit as x approaches infinity. In fact, they stated that as x approaches positive or negative infinity, it will be 0. So what this says is that for any value over x, we can say such as in this term, 1 divided by x squared, that is approaching 0. Because this x reduces to 1 in the numerator over x, this is also approaching 0. This reduces to just 1 over 1, which leaves us with just 2. In the denominator, x squared divided by x squared leaves us with just 1 over 1. This will reduce to 1 over x. And again, that is heading towards 0. And 2 over x squared. Again, even though it's not a 1, anytime that you have just a value divided by x squared, you're going to be heading towards 0. So out of this whole thing, we end up finding that our limit as x approaches 0 is, in fact, 2. And that matches our guess. So that's good. Because there isn't a variable next to 2, if it was 2x or something like that, because of that, we can comfortably say that our horizontal asymptote is at 2, regardless of which way x is approaching infinity. So x is approaching negative infinity for our function, it's 2. As our limit of x is approaching positive infinity for our function, it's 2. That means that on our Cartesian plane, at 2, we have that horizontal asymptote, which the graph of our function is approaching. We don't know what's happening in the middle, but it is approaching that value of 2. So that is our horizontal asymptote. So we found the vertical asymptotes at x equals 1 and x equals -2. And we would say that our vertical asymptotes as an equation are going to be when y equals 2. Well, thanks again for watching. I hope that helps.